Okay, everyone, I'm going to explain the phenomena of seasons. First things first, we know that Earth orbits the Sun. Earth's orbit around the Sun is also called a revolution. So I've got my Earth here and my Sun. So as Earth is orbiting around the Sun, we call that a revolution. And that takes about a full year to complete, so roughly 365 days, unless you have a leap year. Anyways, rotation, on the other hand, is Earth's spin per day. So you have daily spin, which takes about 24 hours. We call that a rotation. And then Earth's spin around the Sun, we call that a revolution. Now, when you think of seasons, you might think seasons are related to how far Earth might be from the Sun. I mean, that would make sense if you were to think about it logically in a way. If the Earth is closer to the Sun, then it must be summertime, because if we're closer, then it's getting hotter. And if Earth is further away from the Sun, then it must be winter. But that's only partially correct. If you lived in the southern hemisphere, so, I don't know if you can really see it, so maybe we'll go with Australia. That's a good one. That would be kind of correct, but we live on the northern hemisphere, so it's opposite for us. And let me draw that out so that it makes sense. Okay, so when it comes to Earth's orbit is not a perfect circle. In fact, it is what we call it an ellipse. So let me draw it out for you. So we have our Sun, and we have, okay, my drawing skills are not that great, so just bear with me. But I'll draw that in blue. Here's our Earth, and here's our Earth. There are points where Earth and its orbit are closer to the Sun. So we can look at distance from here to here, and we can look at distance from here to here. So the point where Earth is closest to the Sun is called perihelion. Perihelion. And that is pronounced like this. Perihelion. Perihelion. And that means Earth is closest to the Sun. Closest to the Sun. Let me do that here. So when it is closest to the Sun, it is actually right there. Then you have the opposite. You have, let me grab another color. We'll go with gray. No, not gray. You might not be able to see that. We have the opposite, aphelion. Aphelion. Oops, that's an N. Aphelion. Okay. And that is when Earth is farthest away. So perihelion would be closer, and aphelion would be at its furthest point away. Many people believe that Earth is closest to the Sun when it is summertime. So they think that this would be summer, and they think that this would be winter, when in reality that's not the case. That is wrong. Wrong. Let me show you. So here's our Earth. And let's say it is summertime on the northern end, and we have our, there we go, on the southern end. So here's us. And we're gonna get an airplane. It's a very sad airplane, leave me alone. We can, in the United States, fly around to the southern hemisphere to maybe Australia. And when it is summer for us, it is actually winter for Australia. And we can actually do this. We can get on an airplane in July. So I'll put July here. We can get on an airplane in July from the United States, and we could fly over to Australia, and it will be cold, and it will also be winter time. But logically, this doesn't make sense. How can we have two different seasons going on Earth during the same day? So we need to think about space from two viewpoints. We need to think about space from the, let's think of it from the straight down model. And we need to think of it horizontally. So we are looking straight down, and then we're going to look directly at it. So in our straight down model, we have our sun, and we have Earth orbiting the sun, okay? We need to look at Earth's orbital axis, which actually, if I were to draw that out for you, Earth does not rotate about a 90-degree angle from its equator. And this here, this is the equator. This is not Earth's axis. Earth actually orbits at an angle. In fact, that angle between the perpendicular plane and the actual plane that we have here is 23.5 degrees roughly. It fluctuates over time, and that's okay. But because of this, and I'm going to go like that, because of this tilt, it actually has huge effect on our seasons. And let's look at that. The seasons are determined by what direction Earth's axis is facing the sun. But in order to really understand this, we have to look at how sunlight coming from our sun, and that's in yellow, so you probably can't really see that. Let me do that in orange. So sunlight from our sun comes in all directions because nothing is blocking our sun. Okay, and if we have our Earth, I'm going to draw it in 2 points. I'm going to draw it here, and I'm going to draw it here. So Earth's axis would be like this, and would be like this if we were looking straight down. Actually, no, that's not right. It would be more like this if we looked at it straight down, technically. If we were going to look at our horizontal model, here's our sun, and we have our Earth, and the apparent path that Earth orbits around, and our sunlight going in all directions. So we're looking at it straight across. That's how our axis would be. Our axis would be like this if we were to look at it straight across. Now my drawing skills are not that great, so I don't want to hear it. So disregard the green line there. We're just looking at the purple ones. This is how our axis would be. Okay. So in order to fully understand how the axis is affecting our sunlight, let's get a clean piece of paper. Let me draw that again really quick. Straight down. And I'm going to draw the sun in orange. So we have our sun, and light is going in all directions. And we have Earth's apparent path, and we have our Earth, and we have our Earth, and you have your axis, and you have your axis, and then you have the horizontal. So we're looking at it straight across. So we have our sun, apparent path that Earth orbits around, our Earth. There we go. We need to look at exactly how sunlight strikes Earth's surface. So let's take our Earth, put the actual axis, and Earth is turning, so I'm going to go like that so that we know Earth is turning 23.5 degree axis. Okay, let's look at this side first. So this picture here, we're going to look at this Earth from our straight down model. Here I have sunlight coming from the left, so I guess I should put sunlight coming from the left. That means that sunlight is striking Earth's surface on this side here. And very lightly, I'm going to put black lines so that we know this is shaded. Earth, the seasons are determined based on which side of Earth is facing the sun with respect to the axis. I've drawn the axis here, and I've done it so that it matches our straight down model. There are places on our Earth that always get sunlight, and there are places on Earth that don't really get sunlight at all. So let's take a look at our Arctic Circle. The Arctic Circle is going to be about here. So we're looking at the really northern end. So we're looking at pieces of Alaska. So Alaska, parts of it, is in the Arctic Circle. And that is areas where, in this example, gets no daylight, because it's on the all shaded side. So if you were to go to Alaska when the Earth is on this side, the sun would never come up. And we know that because we can get on an airplane and we can go to Alaska and we can observe that. Now you have the opposite down here. There are places, well, it's mostly Antarctica, where down here it would always be summer. Or I'm sorry, it would always be sunlight. So I'm going to put all daylight. Okay, so we're just looking at two extremes. We're looking at the two poles. Let's look at our perspective coming from California. First thing, let me attempt to draw, I'm going to do that in green. It's not the best, but there it is. Here is our equator. And the equator, we should know, is the dividing line between the northern and the southern hemisphere. Okay, so for us, let's do, I don't want to do orange, let's go with red. We are going to be in California somewhere right around here. So if we were orbiting around on Earth's axis, we would have daylight. So this would be like morning, then we would have noon, then we would have our evenings coming around, and then we would come around, so it's nighttime, 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 back to morning. And it would just continue. Morning, afternoon, evening, nighttime, it's midnight, comes around, morning, that's our cycle. Same thing happens down here. Draw that in a different color. Again, my drawing's not that great, but here it is. So this would be California. Sure. And this would be Australia. Now let's take a look at this perspective. Just looking at half of Earth, would you agree that we have more time on the shaded half? So where it's nighttime, would you agree that there is more time on the shaded half than there is where sunlight is striking Earth? If you would agree, and I agree too, that would mean that it's winter in northern hemisphere, excuse me. It's winter time. But if you look at the opposite here in Australia, would you agree, based on this model, there is more time spent in the lighted side where sunlight is striking Earth than there is on the shaded side here? If you agree, and I would agree, that Australia would be experiencing summertime in the southern hemisphere. It would be summertime, and I would agree. But now, okay, so I've drawn that out from this perspective, so that means that if this is our pole, this half would be getting sunlight, and this half would not. In our straight down model, now if we were to take this one, now we have to make sure it matches. Sunlight is coming from the left. So this would actually be a diagram on this side in our horizontal model. So if you extend your daylight lines out, this half would be lighted, and this half would be shaded. Okay, so now we need to look at the opposite. And I've kind of run out of room, so let me just go like that. I know my drawing skills are sad. I don't want to hear it. Okay, so we've got our and then here's our equator. So now we need to look at Earth from the other side. So on this side, we have sunlight coming from the right side. So we need to put our sunlight on the right side of our Earth, which means that it is striking this half of Earth's surface, and that means that this half is the half that's shaded. So now let's go back to our Arctic Circle, or Alaska. Let's go back to Alaska here. Our Arctic Circle, it's not a perfect drawing because I can't draw very well. Earth is turning about its axis. So Alaska, from this point, would get only daylight, so no nighttime. So Alaska gets all daylight, or I'm going to say no nighttime. No night hours. Because the path that Alaska appears to rotate around is all on the lighted half, not the shaded half. Whereas the opposite happens down here. Antarctica, so let me write that down. Antarctica would get all night hours. And let's go back to us we would, okay, so we're going to come around, it's nighttime. We would come around, still nighttime. Now it's morning. Now it's noon. Come around. Here is afternoon. Now we're in the evening. Sun comes up, sun stays up, noontime comes around, back to nighttime. This is our apparent path. Where if we were to look at Australia, it would do the same kind of path. Something like that. So this would be California. This one would be Australia. Now let's take a look. Would you agree with just looking at the lighted half that California or the United States, whichever one you prefer to use, spends more time in the half of Earth that's getting illuminated from the sun as compared to the backside? If you agree, and I do too, oh, and I didn't write that down. This is the northern half, and this is the southern half. This would be our summer. And the opposite holds true here. Would you agree that Australia has less time in the daylight and more time at night? I would agree. This would be their winter. So if we were to go back to our straight down model, this half would be getting sunlight. This half would be dark. And if we were to look at our horizontal model, this half would be getting daylight. This half would be getting nighttime. Okay, but I've only talked about 2 seasons. I've only talked about wintertime. And I've only talked about summer. Well, what about the other 2 seasons? Let me go to another page. So let's go back to our straight down model. Let's talk about the other 2 seasons. So first, let me put our sun. And sunlight illuminates in all directions. There is nothing that is blocking the sun. And we have our apparent path that Earth is orbiting around. So we have our Earth here, and we have our Earth here. And we have already established that if our axis is pointing this way, and our axis is pointing this way, this half of Earth would be illuminated, and this half of Earth would be illuminated. This side would be dark, it's away from the sun. This side would be dark, it's away from the sun. So this would be our winter, and this would be our summer. So let's look at the other 2 seasons. So I'm going to put our Earth here, and I'm going to put our Earth here. Now the direction that Earth's axis points does not change, so it's still pointing in the same direction. And Earth actually orbits around the sun counterclockwise. So if we were coming from winter, and we know that it moves opposite the way the clocks do, this one is going to be springtime. These 2 are a little bit hard to draw without having a 3D model. And then from here to here, we go from spring to summer, from summer to fall, and from fall to winter. Within these 2 points, we have something called a solstice. The solstice has to do with how many hours there are in the daytime. So for summertime, we have a June solstice, or summer solstice, and that's on or around June 21st. And we have the opposite in winter time. So our winter solstice is going to be on or around December 21st. The solstice is so we have our longest day of the year, and we have our shortest day of the year. And in between the two, we have something called an equinox. And an equinox is when there's equal time, meaning we have 12 hours of daylight and we have 12 hours of nighttime. And the same holds true here. So you have 12 hours of day and you have 12 hours of night. So now I want you to think about this rotationally. So if we go from the winter, so we go from December, so from December, the equinox is about March 20th. So our days are getting slightly longer and then they become equal. And once our days get equal, then they got to get longer and longer and longer and longer and longer till we reach our summertime or our summer solstice, which is the longest day of the year. And then the days start getting shorter and it comes all the way down to our equinox again. This one is in September, on or around September 22nd or 23rd. That's always easy for me to remember because my mom's birthday is September 23rd. Okay, and then so from here, our days are getting shorter and shorter and shorter until we get back to our winter solstice. We are somewhere in between these 2 points here.